You are welcome to this session of Vector Calculus, and under this session we're going to look at double integrals. We're going to look at double integrals or double integration. And so double integration geometrically measures the volume created by a surface area over a region of integration. And so the definition of double integral, which we said measures the volume, is this double integral about a region of the surface area f of x and y dA. And so we can, since the A, it measures the area over which the surface area at, we can always put the A into two forms. Either it is f of x, y, dx, dy, or the double integral can be by the same region, f of x, y, dy, dx. In this case, the region, R being the region of integration, most often lies in the OXY plane. And so once it lies in the OXY plane, the area can be separated into the area along the x and then the y. Or you can work along the y and the x. Both of them will give you the same answer. We all arrive at the same answer. And so we'll have to formulate what we call the iterated integral in order to be able to calculate the double integral, which geometrically we said that it measures the area under the surface, that's the height times the area. And we know the basic definition of volume is the height times the base area, or the base area times height. And so before we proceed, we have to look at the form of the region of integration. There are basically two types. We're going to look at the first type. This one can go. The first type is type 1, which is R, where it is rectangular form. And then we'll look at situation where the region of integration, which obviously lies on the OXY plane, where R, the region of integration, is non-rectangular. It's a non-rectangular form. And so in each of these cases, we need to formulate the iterated integral depending on the nature of the rectangular area of this integration. And so we'll take the first one where our region of integration is rectangular, and then we'll take an example. After that, we'll look at the non-rectangular form of the region of integration. So the first one can go off. So if you have the region of integration, which is rectangular, which means we have x greater than x1, and then less than equal to x2, and then we'll have our y greater than equal to a certain y1, less than equal to a certain y2. So what we have to do is that in these cases, it becomes very easy to understand when we sketch the region of integration. And so we sketch it. This is in the OXY plane. This is the y-axis, 0, and this is the x-axis, sorry, and this is the y-axis. So if you are talking of the region R, x between x1, assuming this is x1 and this is x2, and then y is between y1 and then y2. So in this case, we can see that our region of integration is a rectangular, it's a rectangular form, and this is the region of integration. And so once we have been able to actually picture how the region of integration will look like, now the next is to formulate what we call the iterated integral. Iterated integral. And so the double integration, which is about the region R of f of x and y dA, where in this case f of x and y, where f of x and y is the surface area, which invariably gives us the height. And so this is the base of the region, and then the height is given by z, which is equal to a function in what, x and y. And so from here we're going to formulate the iterated integral. So we can have the double integral, we can disintegrate the a, we can dA into the x times the y. So let's proceed with the x dy. And when we are done with that, we'll formulate the iterated integral where we have the a put into the y and what, the x. And so what happens with double integral is that we work within the inner integrand. We do the inner first before we do the outer. So in this case, the inner integration will be with respect to x. And so our x, if x starts from, see, when we take a small strip, delta s1, under delta s2, delta s3, small s, so that our strips are moving from the lower limit of x, which is x1, and then we are moving to the upper limit of x, which is x2. So this type of integration, we start from x1 and end at x2. So when we finish the small strips, we say that for this kind of slide, we're going to have this. And when we proceed along the y-axis, we see that then we move the whole strip along the y-axis, which means that we are moving from the y, which is the lower one, which is y1, and we go to the upper limit of y, which is y2. And so this is how we formulate the iterated this integral. Now the second part is when we also want to formulate the iterated integral first along the y-axis. So our double integral now becomes f of x, y, dy dx, which means that we start with the inner integrand, which is respect to y. And what do? We take small values of dy, that is dyi. So we start from the lower y, which is y1. We take small dyi, dy2, dy3, all along the y-axis. So it means that our y starts from y1 to y2. And when we finish with this strip, and we replicate it for the next slides of this, so that we see that we then move all of them along the x-axis. So this one will be x1 up to x2. So in each of these situations, we can always calculate the double integral. Either we start from the x and we do the integration from the inner part, or we start with the y where we do the integration the inner part. We'll always get the same answer. So quickly, let's take an example to illustrate how to find the line integral along each of the path. So let's take an example. So this one can go off, one can go off. So we take an example to illustrate how to find the double integral when our base is a rectangular base. That's the region of integration is rectangular. So let's take example 1 for example. We have evaluate the double integral f of x, y, d, a, r, given f of x, y will be 3x plus 4y, and r lies in the region s is greater than equal to 1, less than equal to 3, and y is greater than equal to 0 and less than equal to 2. So in this situation, to solve it, we need to sketch the region of integration. And so the region of integration will be, this is the x-axis, this is the y-axis, 0. So along the x, the lower limit is 1, assuming it's 1, upper limit is 3. And then for the y, on the y-axis, the lower limit is 0, and the upper limit is 2. So it means that if you sketch this one, our region of integration is going to be like this, R. This is our region, that's our region of integration. So we have the choice either to work along the x-axis or the y-axis. Each of them will give us the same answer. So let's work along the x-axis, right? So our double integral about r of f of x and y, f of x and y is giving us 3x plus 4y dA, which we can put it into this form, 3x plus 4y. dA, we're working along the x-axis, so the A will be the x dy. Now the iterated integral, since we are working with x first, the lower limit of x will be 1, and the upper limit of x is going to be 3. And then we do the inner integration first. The inner integration, where the integrand, we integrate with respect to x. And then when we finish, we integrate the outer one with respect to y. In such a situation, y moves from 0, the lower limit of y is 0, and the upper limit of y is 2. So now we are ready to integrate. So integrate the inner one, 0 to 2. Now we are integrating with respect to x. So let's keep note that y is a constant. We treat it as a constant. And so if we integrate 3x dx, we have 3x squared over 2. Plus, if you integrate 4y dy, if you integrate 3x with respect to x, we still have 3x squared over 2. Now, if you integrate 4y dx, 4 is a constant, y is a constant. So if we integrate a constant with respect to x, we give it the same constant, 4y times x. And the limit is from 1 to 3. When we finish with this one, multiply, we find the y. So let's put in the upper limit. Let's put the upper limit, 0 to 2. Upper limit is x, which means that is x equal to 1 and x equal to 3. So it means that where you see x, we are going to replace x with 3, the upper limit. So let's go. So we're going to have 3 times x. X here is 3 squared over 2 plus 4y times 3. That does it for the upper limit. Now we're coming to the lower limit where x equal to 1. So we put 1 here. We're going to have 3 times 1 squared over 2 plus into bracket 4 times y times 1 or dy or dy. So if you tidy up, from 0 to 2, what you have is 3 squared is 9. 9 times 3, 27. So we have 27 over 2. 27 over 2. And this one will give us plus 12, 3, 4, 12y. Then minus 3 over 2. Then another minus 4y or dy. We can still further tidy up. We have integral from 0 to 2. 27 over 2 minus 3 over 2. That will give us 24 over 2. 24 over 2 will give us 12. Now we have 12y minus 4y. So if we take 4y from 12y, we're going to have 8y or dy. Now we are going to integrate this term with respect to y. And so this one becomes constant. If you integrate 12 with respect to y, we have 12y. Plus, if you integrate 8y with respect to y, we're going to have 8y squared over 2. And the limit is from 0 to 2. So we can still tidy up. So we have 12y plus, this one going into 2, 1, this one into 4. So we're going to have plus 4y squared, 0 to 2. And so we put the limit. The upper limit is 2. That where we see y, we put 2. So we're going to have 12 times 2 plus 4 times 2 squared. Now, if you put the lower limit, which is 0, everything becomes 0. So when we tidy up this one, we're going to have 24, 12 times 2, 24, plus 4, 2 squared. 2 squared is 4, 4, 16. So if you add 24 to 16, then we're going to have 40. 40 square, cubic unit, because a volume, cubic unit. Whatever unit is given to you, then the answer will be 40 cubic units. That is, we'll work along the x-axis. We also look at a situation where we can work along the x-axis, and we get the same the y-axis this time, so we can get the same answer. So let's quickly take this one off, and then we work along the y-axis. So we are going to work the same example, but this time along the y-axis. So this one can go off, and then we'll work along the y-axis. So along the y-axis. And so our double integral, our r, f of x and y, which is give us 3x plus 4y, dA now becomes double integral 3x plus 4y, this time dy dx. So in formulating the iterated integral, we are moving along the y first. And so y, we move from y starts from 0 and then ends at 2. So the lower limit is 0 and the upper limit is 2. And then when we finish, we'll move the whole strip along the x-axis. And so x-axis starts from 1, 2, 3. And so now let's do the integration. So from 1 to 3. We are now going to integrate respect to y. So it means that x will stay as constant. I think we are all aware. So let's integrate. So if you integrate 3x respect to y, you're going to have 3xy plus, if you integrate 4y respect to y, we're going to get 4y squared over 2. And the limit is from 0 to 2, all dy. So we can tidy up a bit, or this one will go here 1, this one will go here 2. And so upper limit is 2. So it means that we are going to put x equal to 0, x equal to 2. So x equal to 2. So where we see x, we put upper limit, we put 2. So x is here. So we're going to have integral 1 to 3, x is 2. So 3 times 2 will give us 6. 6 times y will give us, we are integrating with respect to y. And so our limit is y equal to 0, 0, and then y equal to 2, y equal to 2. And when we finish, we do the integration with respect to x. So the upper limit is y equal to 2. Where we see y, we put 2 there. So we're going to have 3 times x times 2, which is 3 times 2 will give us 6x plus, we have reduced this one to 2. So this one becomes 2y squared. And so plus 2y squared. Y is 2 times 2 squared. And then we'll do the lower limit. The lower limit is 0. So it means that when you put y equal to 0, here will be 0, here will be 0. So there's no need. So this one times dx. And so when we tidy up 1 to 3, we're going to have 6x plus 2 squared is 4. 4 times 2 is 8. 8 dx. So now we are going to integrate with respect to x. So we're going to have 6x squared over 2 plus 8x. The limit is from 1 to 3. And so when we tidy up, we're going to have this one 1, this one 3. So we're going to have 3x squared plus 8x, then 1 to 3. So let's take the upper limit. Upper limit is 3. So we're going to have 3 times 3 squared plus 8 times 3 minus lower limit. Lower limit is 1. So 3 times 1 squared, then minus 8 times 1. So we're going to have 3 squared is 9. 9 times 3 is 27. 27 plus 3 times 4, 8 times 3, 3 is 24. 24 minus 1 squared is 1. 1 times 3 is 3. Minus 8 times 1 is 8. So we're going to have 27 plus 24. I guess that will be 51. 51, yes, 51. Minus 3 minus 8 will give us minus 11. And so 51 minus 11 will give us 40. We realize that 40 cubic units. We realize that the answer along the x-axis gives us the same as when we worked along the y-axis. So there's no need to do the two. So either you choose, per your choice, choose to work on the x-axis or you work on the y-axis, you get the same answer. And so we are going to look at the second scenario where the region of integration is non-rectangular. So we quickly take this one off and take a situation where we are dealing with non-rectangular region. And so quickly, this one can go off. This one can go off.